Okay, the last section in Chapter 6 is solving trig equations. So like the last section, 6.3, this is the exact same thing. Same identities are being used. The only difference with this one is now you're actually going to solve for the variable that's there. So whether it's x, y, theta, or whatever, you're actually going to find the answer for it. And most of the time when we do this, you're going to be using one of the special triangles or the unit circle to find your answer, because most of the time these are going to be asked for you to find in exact value. So the first one here says solve over 0 is less than or equal to x is less than 2 pi. So that means our answer has to be between 0, and it can include 0, and up to 2 pi. So we have sine 2x minus cos x is equal to 0. So sine 2 cos x is the double angle identity for sine. So looking off of your sheet, we know, or if you remember it, this is the equivalent of 2 sine x cos x minus cos x equals 0. So what we need to do then is we have to do just like we did with any polynomial functions that we worked with before. You have to factor it and then put your factors equal to 0. So between 2 sine x cos x minus cos x, I can GCF a cos x. And I'm left with cos x times 2 sine x minus 1 is equal to 0. So I have my two factors. So I say cos x is equal to 0 and 2 sine x minus 1 is equal to 0. So cos x is equal to 0. I know I can't use a triangle for that, so that means I'm going to use my circle. Cos x is the same as the x variable. The x variable is at 0 here and here, which means it's at 0 at pi over 2 and 3 pi over 2. So now for the second factor, I have 2 sine x minus, equals 1, because I'm going to bring that 1 over, divide by 2. So sine x is equal to 1/2. So I have to think about my triangles to decide, okay, which one uses 1 and 2 as a ratio for the sides. That comes from the 30, 60, 90 triangle, where I have 2, 1, square root 3. This is pi over 3, and this one is pi over 6, or this is 30, and this is 60 degrees. So sine is opposite over hypotenuse. So opposite, to get opposite over hypotenuse, I'd have to be using the pi over 6. But using my cast rule, I know that sine is positive in quadrant 1 and also in quadrant 2. So that means that it would be here, but also as a reference angle with pi over 6. So that would make this 5 pi over 6. So I put in then my final solution. It's pi over 6. Pi over 2. 5 pi over 6 and 3 pi over 2. What you should always do is check them to see if there aren't any that won't work. So you have to see if, so I know pi over 6 works for sine, but will pi over 6 work for cos? Well, in this case it can, because cos would just be adjacent over hypotenuse, so that works. Same thing with 5 pi over 6, so if it worked for pi over 6, it'll work for 5 pi over 6. And you have to check then pi over 2 into sine. So if I think of my circle, or if I think of sine of pi over 2, and where am I? 90 degrees, can I find one where it equals 90? Yep, that'll work. So you can check them in your, either doing what I just did, or you can check them in your calculator. And if you get an error for any one of those, then then it's not a solution. It has to be a solution for both in order for it to be a solution for the equation. So the next one, 2 cos x plus 1 minus sine squared x is equal to 3. So I take a look at my equations here. I know there's nothing I can do on the right side of the equation, so I take a look at the left side. So 2 cos x plus 1 minus sine squared x. Well, 1 minus sine squared x, if I think about my Pythagorean identity, that is the same. If I look at 1 minus sine squared x, if my Pythagorean identity says cos squared x plus sine squared x is equal to 1. So if I move that over, cos squared x is equal to 1 minus sine squared x. So when you're solving these, you always want to either have all sines or all coses. I went with the all cos. So 1 minus sine squared, I'm going to substitute into there. So this will be 2 cos x plus cos squared x is equal to 3. Sorry about the pause. Just had a little coughing fit again. So if I try to do this, what happens is I'm left with cos x times, or if I try to GCF out of here, cos x, I'm left with 2 plus cos x. Or you can't do anything with that. So what I really want to do then is just leave this the way it was, and bring that 3 over, and then treat it as just a regular polynomial. I'm going to put this in order though. I'm going to start with my, highest power. So cos squared x plus 2 cos x, and if I bring that over, this will be a minus 3. Because if you remember, when you're solving with equations, you always want your equation to equal to 0 so that you can find the answer. So if I use my substitution method, instead of saying cos squared x 2 cos x, I'm going to say let y equal cos x. So that means this is going to be y squared plus 2y minus 3 is equal to 0. Using product and sum, that means that this is going to be excuse me, y plus 3 times y minus 1 equals. So now I can substitute back in. So this is actually cos x plus 3, and this is cos x minus 1 equals 0. So cos x plus 3 equals 0. Cos x minus 1 equals 0. So this would be cos x is equal to negative 3. And I know from when I graph these that if I were to graph cos x, it's always in between 1 and negative 1, right? My amplitude, it goes from 1 and then it goes down to negative 1 and then back up. So it can never be a negative 3 unless there was a 3 in front of the cos right here, but there isn't. So that means that we reject this one. I hope this is okay, because it kind of sounds to me like there's a little feedback or something. The second one, cos x is equal to 1. So where does cos x equal 1? It's in that unit circle again. And you might have thought, why didn't I use the 45, 45, 90? Because there are 1s in there. But no matter what I do, I have to use that hypotenuse for an adjacent. So that's why I don't even bother trying that one. So cos x is equal to 1. That's when the x value is equal to 1. And that only happens right here. So that means that x is equal to 0. I don't use 2 pi because of my restriction right here. So that is my one and only solution. Okay, next one. Sine squared x is equal to 1/2 tan x cos x. Okay? Well, first of all, what you should clue into here is you have a tangent. I haven't worked with tangents, or we don't work with tangents when we're solving. We always want sine and cos. So that's the first thing I'm going to do, is take care of that tangent. I have sine squared x is equal to 1/2. Tangent is sine over cos, and then times my cos x. So that means I can cancel these two. So I have sine squared x is equal to 1/2 sine x. So I have to bring everything over to one side, so I'm going to go sine squared x minus 1/2 sine x is equal to 0. I have two sine x's in common in both of these terms, so I'm going to take a sine x. So I have sine x minus 1/2 is equal to 0. So my two factors, sine x is equal to 0, sine x minus 1/2 is equal to 0. So sine x is equal to 0. Thinking of my unit circle, sine is 0 here, and it's 0 there. So that means that it's at 0 and pi. Sine x is equal to 1/2. Well, from just above, the example above, I found out that that's at 5 pi over 6 and pi over 6. So you can do a check to see if they work in both, and of course since they're both sine, they'll work fine. So my solution is 0, pi over 6, 5 pi over 6, and pi. Okay, next one. Cos 2x is equal to cos x. So I'm going to bring everything over to one side first. So cos 2x minus cos x is equal to 0 is where I start. Now cos 2x is the same as, if I'm thinking of my, there's three choices of identities for the double angle of cos. I don't want to use the one with sine in it, so that means I'm going to substitute this with the 2 cos squared x minus 1, and then minus cos x. If I rearrange this, I have 2 cos squared x minus cos x minus 1 is equal to 0. So it's a polynomial. Again, if I let y is equal to cos x and substitute, I have 2y squared minus y minus 1 is equal to 0. So using slide and divide, I have y squared minus y minus 2 is equal to 0. If I factor that, excuse me, that's y minus 2, plus 1 equals 0. Divide through by 2. This will be y minus 1, and y plus 1/2 is equal to 0. Yep. Now at this point, if you wanted to, you could go multiply your 2 through, so that this is 2y plus 1. But when it comes to solving it, you're going to have it, it's going to go back into a fraction anyway, so you can just leave it there and just substitute your cos in. So cos x minus 1 is equal to 0, and cos x plus 1/2, whoops, is equal, are equal to 0. I said equal to 0 twice, I think. So cos x minus 1 equals 0. Cos x plus 1/2 is equal to 0. So cos x equals 1. Cos x is equal to 1. Do I have that here somewhere? Yep. Right above here. If I use using my unit circle, I found cos x is equal to 0. Or sorry, is equal to 1 only at 0. So this one is x equals 0. This side then is cos x is equal to negative 1/2. it's at negative 1/2. That's using your 30, 60, 90 triangle. So cos is negative in quadrant 2 and quadrant 3. Whoops, pretend those are the same size. This is my 2's go here. Using this angle, the adjacent side has to be negative 1. So then that means that this side here is square root 3, but we don't really care about that. So that means that this angle here, in order to use that ratio, it's going to be a pi over 3. So my reference angle is pi over 3, or 60 degrees. So that in that case then, in this quadrant, that would be pi minus pi over 3, so that's 2 pi over 3. And in quadrant 3, it would be pi plus a pi over 3, so that would be, 4 pi over 3. So you can check those answers back in, and they work. So x is equal to 0, 2 pi over 3, and 4 pi over 3. And those are all within the restrictions, so they all work. Okay, last one. 3 cos x plus 2 is equal to 5 secant x. So again, we have a secant in here. We only want cos and sine, so that's the first thing we're going to do. 3 cos x plus 2 will stay the same for now. 5 secant x, that's the same as, secant is the same as 1 over cos. So this is the same as 5 over cos x. So I need to get rid of my cos x, so I'm going to multiply everything through by cos x. I don't want that denominator. So this will become 3 cos squared x plus 2 cos x, and this cos x and that multiplying by 1 will be gone, so that will just be a 5. So if I bring it over to finish solving my equation, 3 cos squared x plus 2 cos x minus 5 is equal to 0. So I use my substitution, so this is easier to solve. So this is 3y squared plus 2y minus 5 is equal to 0. So slide and divide, I move my 3 over, so this becomes y squared plus 2y minus 15 equals 0, product and sum, y plus 5, y minus 3 is equal to 0. So now I divide through with my 3. So y plus 5/3 and y minus 1 is equal to 0. Now again, I'm just going to leave this as 5/3 because if I go to solve further, I'm just going to have it back into a fraction. So this then is going to be cos x plus 5/3 is equal to 0. And then cos x minus 1 is equal to 0. So cos x is equal to negative 5 over 3. And again, just like in the other example, remember when you draw on a regular cos x with no transformations done to it at all, it can't be a negative 5/3. It can only be a negative 5 or a negative 1. So this is a rejected one. Cos x is equal to 1. Cos x is equal to 1 on that unit circle again, only at x is equal to 0. So that is your solution. So that's it for this section. So again, the biggest thing to remember is that you only want to solve in sine and cos. And when you have both sine and cos in there, you see if there's something you can do to manipulate the equation so that you are working only with sine or only with cos. And then do any factoring if you need to, and solve. So your assignment there is at the bottom of the page, 320, questions 1 to 11.